In this video, we are going to be solving a few static equilibrium problems. So the definition of static equilibrium is that it's when an object is at rest and the net force acting on it is zero. Remember, the net force acting on an object is zero even when the object is moving at a constant velocity, and that is called dynamic equilibrium. So sample problem 1 is pretty simple. This box is stationary and hanging from the ceiling. Give me 1 second. Okay, if the tension in the string is 28 newtons, find A, its weight, and B, its mass. So you don't really have to draw a free body diagram for this one, but it's probably a good idea to get into the habit. So you're going to have the tension pulling up, which is 28 newtons, and then you'll have the force of gravity pulling down. Remember, the force of gravity is its weight. So the tension will just be equal to the force of gravity since the net force acting on it is zero, and those two forces are in opposite directions. So T is equal to Fg, and to get Fg, we just do the object's mass times its gravity, but we already have the number for tension, so it's going to be 28 newtons. So this is our final answer to part A. For part B, we know that Fg equals mg, and we figured out in part A that Fg is equal to 28. So 28 equals 9.8 times m. Divide both sides by 9.8, and you get that m is 2.86 kilograms. So this is our final answer to part B. Sample problem 2 is another pretty simple one. This box has a mass of 4.3 kilograms. If it is hanging from the ceiling and is at rest, what is the tension in the string? So basically for this one, we're doing the opposite of what we did for the last one. So we know that the weight is equal to mg, and if you think about the last one, we know that Fg is pulling down and the tension is pulling up, and since the box is at rest, again, the tension will have to be equal to the force of gravity. So the weight is 4.3 times 9.8, and that'll be equal to 42.14 newtons, and T is equal to Fg. So the tension is equal to 42.14 newtons, so that is our final answer. I call these double tension problems. They're a little bit trickier. So again, this picture is hanging, and there's maybe a string here and a string here. It's a picture hanging on a wall, so you would hope it would be at rest. Because it's not swinging back and forth, you know that the x components will be equal to each other. And then you know that the sum of the y components will be equal to the weight. So that's one x component, and that's another x component. They have to be equal to each other. And then this is the y component of tension 2, and then this is the y component of tension 1. This plus this would have to equal to the weight of the object. So our goal here is to find the weight of this picture. The notation I'm using here is pretty simple. So we have the y component of tension 1 plus the y component of tension 2 equals the weight. And since we're pretty familiar with vectors now, this should be pretty easy. The y component of tension 1 will be 50 sine 30, and it'll be the same thing for tension 2, since the two tensions are equal to each other. And if you just plug those numbers into your calculator, you'll get 25 plus 25, which is equal to 50 newtons. So the answer to this is 50 newtons. That's the weight of the picture. I have one more sample problem for you. It's another double tension problem. We want to find the tension in each string if the picture has a mass of 2.2 kilograms. So again, for this one, it's not swinging right to left. So in the x direction, the tensions will balance out. And again, the y component of the two tensions in tension 1 and tension 2 will have to be equal to the weight of the object pulling down. We know that the weight of the object is equal to mass times acceleration due to gravity. And we're given the mass of the picture, it's 2.2. So to get the weight, we just do 2.2 times 9.8, which is 21.56. Now we can use our knowledge from the previous problem and say that T1y plus T2y is equal to Fg. This time the angle that we're given is 60 degrees, so the y component of tension 1 will be equal to whatever the tension is times the sine of 60 degrees. We also know that T1 equals T2. So, since T1 equals T2, we can just double one of the tensions to get them added together. So now this is pretty easy to solve. We can just divide both sides by 2 and by the sine of 60. And we end up with the tension in each string is 12.45. Now how did I know that the tensions had to be the same? I knew that because the angles were the same. So this is how you do static equilibrium and tension problems.